Welcome class to our guided note session on Skill 7 from Unit 5. In this outline we are going to take a look at the number e and also what's called the natural logarithm. So you're probably thinking, Ms. Lasner, e is not a number, it's a letter. And I would say yes, you are correct. But like pi, it's a letter that has been assigned to a particular numerical value. But let me give you a little bit of background before I tell you exactly what that value is. So the letter number e, is thought of as the base in an exponential or logarithmic function that represents the growth of a process or a quantity that grows continuously in proportion to their current quantity. When the rate of change of an amount, so an amount is growing at a rate that is proportional to how much it currently has, like population, for example. When you could say, okay, the rate of change of population is this particular constant, some constant times the current population. So take our current population, multiply it by such and such constant, and that'll give you your rate of change. And it'll also give you the next quantity, the quantity that this amount is going to soon have. So it's like this proportion between the actual current amount and then the rate at which that current amount is changing. So things that have this type of exponential growth or decay, so that is basically what an exponential growth or decay is. When you take a current quantity, you multiply it by some constant. That's what it means to be proportional. Okay, you multiply it by some constant over and over and over and over, and that shows you the rate at which it's changing as well as the next quantity it's about to have. That's an exponential growth or decay. Okay, so that could be anything from interest on a savings account to bacteria growth in a petri dish or wherever bacteria is growing, to the radioactive decay in different fossils or, elements, to the growth of a population, the spread of a, population, the spread of this coronavirus, this pandemic that's spread globally. And these things can all be modeled using a base of e in an exponential or logarithmic function. Okay, now the number e is what we call an irrational number. So write that in on your outline. It's an irrational number. It's like pi, right? We all understand pi to be 3.1415926, yada, 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 yada. The decimals go on forever. They don't have a pattern. They don't repeat. They don't terminate. Irrational. So the value cannot be written as a fraction. Okay, now sometimes it's referred to as Euler's number. It looks kind of like Euler, but it's pronounced Euler, kind of like our mascot. And so the first letter of his name was E, and therefore that's where we get the name of this number. So it kind of was named after him. He was the one kind of studying this phenomenon where a quantity or a process could grow in proportion to its current quantity. That sort of natural exponential growth or decay, he studied it, and so therefore and he found that this base happened to be the base of these types of functions. They just had a base like with this decimal, which is why it's often referred to as the natural base, because it occurs in nature, the way things grow and spread, or the way things decay or depreciate or deteriorate. All right, so it's an irrational number. Sometimes it's called Euler's number after the famous mathematician. It is used as a base of the natural logarithm. Okay, so sometimes you see this on your calculator or in different textbooks or whatever. The ln of x function is the natural log. That's a log of base e. Now, here's the decimal. So it's approximately equal to 2.7182 .128 ... It's a decimal that doesn't repeat and doesn't terminate, so it continues. And a lot of times when we are working quickly with this function and don't have a chance to punch something in our calculator, we really kind of think of it as just right around 2.7 or even 3. Just to get an idea, just to get a quick idea in our head of the size or value of something, we really kind of round it all the way down to the 2.7 and then really kind of think of it as close to 3. Okay. Now, just a little bit of background on where Euler came up with this decimal is he realized that it was the result of this following limit. So this notation probably looks a little bit strange to you. This LIM is short for limit. And this is saying that if you look at this expression here, 1 plus 1 divided by n, and then that sum, the whole thing is being raised to the power of n, then E turns out to equal what this whole value approaches, the limit of this whole entire value, as this n approaches infinity, and it's positive infinity. So n is getting larger and larger and larger and larger indefinitely. So what I want you to do on your calculators is to evaluate this expression, 1 plus 1 over blank, all of that raised to the power of blank, for these different values of n. So we're going to start small. And then gradually, starting small, so n will be 1 and then 2, and then we're going to start picking up the pace and start letting n really approach infinity, really get big fast. So we'll go all the way to 10,000, and I want you to see what these numbers equal and how and if they are approaching the value of this approximation that I wrote up here. So for this first one, when n is 1, this would just end up equaling 2, because the sum would just be 1 plus 1, and then if I raise that to the power of 1, well, anything to the power of 1 is just itself. So when we start with a small value for n, then we don't get this whole decimal 2.71828, we just get the whole number 2. No decimals. In fact, it's kind of like 2.0000, right? Because it was a whole number 2. Okay. And then this one, when I let n equal 2, I end up with 1.5, right? Because if you add 1 plus a half, it's 1.5 squared, or 1.5 squared. And when I square 1.5, I get 2.25. So it's starting to approach 2.71828. It's getting close. It's closer than 2.00 anyway. It's inching its way, right? It went from 2 to 2.25. Okay, so now let me switch it over to Desmos so we can start looking at some of these larger values. All right, so here I've got my list of the different values just so we can watch and see the trend. And here's the one where n is 10, right? I plugged in 10 into the denominator of the fraction and I'm raising it to the power of 10. So 1.1 to the power of 10, and I get this. So look at that. The decimal place is getting closer to the true value of E, which is that first decimal should be a 7, right? 2.7, blah, blah, blah. We're getting closer. It was 2.0, then 2.2. Now we're at 2.5. Okay, it's building its way up, and n is only at 10. It's not even really getting that close to infinity yet. Okay, I have it jump to 100, so that's quite a distance away from 10. Still a relatively small value when you think about letting it go all the way to infinity, but already I got that decimal place of 7, right? It's really starting to approach that value that we assign E to represent, 2.7. When I let n jump to 1,000, so now I have 1 plus 1 over 1,000 to the power of 1,000. Now I'm getting the first 2 decimal places, 2.71. So now the number is getting closer to the true value of E, which I have up here, 2.71828182846. Of course, there's more decimals beyond that, but this is as far as Desmos can get us, which is even farther than some of our calculators. So that's pretty impressive. I jumped to 10,000, which I believe is where your worksheet stops. And look at that, I have the first 3 decimal places, 2.718. So it's correct all the way up to 3 places. And I thought maybe one more. I'll just jump to 1,000,000. I'll let n equal 1,000,000. And then now I look at this. I have the first 5 decimal places correct. 2.71828. So, and then of course these are not fully correct, but as n gets larger and larger and larger, then the remaining decimal places begin to fill out correctly and bring us to this value that we now refer to as e. So here are those values jotted down on our note outline. And e, the number e, is basically the result of this limit after n has reached infinity. So assuming that we can let n actually equal infinity, okay, it's approached infinity, the value of this limit, once it's gotten all the way to infinity, would equal e. E is the result of this limit. And so by letting n go to 1,000,000, so we're getting closer to infinity, we can see those first 5 decimal places, 2.71828. But what we have to understand is that there will be continuously more decimal places beyond that point, which is what makes it an irrational number. At any rate, that is what the value of e is equal to, and it's already programmed into your scientific calculators. And it's already programmed in as the result of this limit, but we can understand it as equaling approximately 2.71828. So speaking of that function, the function of y equaling e to the x, that would be considered the parent exponential function whose base is e. Now remember, we're going to think of e as about 2.7 when we're working through this. But what we want to do is get a visual of what this graph looks like. So this e, which is the base, is greater than 1, right? Because it's about 2.7. So it should look like the typical exponential growth. And it will look like the typical exponential growth. But just to drive that point home, we are going to go ahead and make a table of values anyway, from -2 through 2, our typical x values that we use when determining a parent function. So I'm going to have to evaluate e to the power of -2, e to the power of -1, e to the power of 0, e to the power of 1, and e to the power of 2. Now, just like any other base, when you raise it to a negative power, you're going to take the reciprocal and square it. So we're going to do 1 over e squared. And it's about 0.14. Very close to 0, very tiny number, very small. When you have e to the -1, we're going to do 1 divided by e. Now this number would be approximately 1 divided by 2.7. So I often think of it as like 1/3. But let's go ahead and get the more exact value right now. And see, very close to 1/3. It's about 0.4, roughly. 0.4. E to the 0 is going to equal 1, because any base to the power of 0 is equal to 1. E to the first power will equal itself, so we'll imagine that, or not imagine, but we will approximate that as about 2.7. And then e squared would equal, it's about 7.4, roughly, about 7.4. Because it would be a little bit less than 3 squared, which is 9, and 7.4 is a little bit less than 9. So these are the values I get when I plug in different exponents, which, by the way, is what makes this an exponential function, because the variable is the exponent, right? The variable is in the exponent spot. E, though you might think it's a variable because it's a letter, it's actually not a variable. It's representing one specific number, one specific constant, and that constant is about 2.7 when you approximate it. So the variable is actually x, and it's in the exponent spot. And as I plug in these negative variables, what I get are actually values that are really close to 0, right? They're not negative because they're what you get when you take the reciprocal of the base. And the base was greater than 1. So when you flip over a number that's greater than 1, it becomes actually a rather small value. So let's plot these points. So at -2, I have a number that's almost 0. It's 0.14, maybe like right there. When I go to -1 for x, I get a number that's a little bit farther away from 0, but not much. It's still less than 1, right? 0.4. When I go to 0, I get a value of 1, which is our standard y-intercept for any exponential function, 0, 1. When I go to 1, I get a value of e, which is a little bit less than 3, right around 2.7. And when I go over to 2, I have a value that's a little less than 8. It's about 7.4. So that goes off my grid a little bit. 1, 2, 3, 4, 5, 6, 7.4, be like right around there. And like all other exponential functions, it has the horizontal asymptote that's going along the x-axis at y equals 0. And it has that typical exponential growth shape since the base was greater than 1. And it's got the typical values of 1, the base, 0, 1, and then -1, the reciprocal of the base, right? 1 over e, which was about approximately 0.4. So you get this kind of shape here. And as x gets more negative, the outputs get smaller and smaller and closer to 0, creating our horizontal asymptote. So the function y equals e to the x has a horizontal asymptote at y equals 0. It has a domain of all real numbers, because I can plug in negative x's, zeros, and positive x's. The range, though, like any other exponential function, is only above 0, strictly greater than 0, because even when I plug in negative x's, my outputs are positive. They're small positives, but they're still strictly greater than 0. It has the standard y-intercept that all exponential functions have, which is 0, 1. And that's because any function raised to the power, any base raised to the power of 0 will equal 1, including e. E to the power of 0 is equal to 1. So remember that. And it's increasing the entire time. It's an increasing function. It's exponential growth because the base e is greater than 1. So I just wanted you to be familiarized with it. I mean, it should hopefully remind you of just any exponential curve because it looks just like any other exponential function with a base greater than 1. But it still helps to kind of put a table of values to it and kind of explore the values. Okay, now a second very important function, which is the log base e. The inverse, if you will. This is the inverse of e to the x. So it's the log base e, but you'll never see it written that way. It's been abbreviated because of this phrase logarithmus naturalis. This is Latin for natural log, and that's how a lot of people refer to it. Oh, the natural log, blah, blah, blah. Well, they took the L and the N from the Latin version of that and abbreviated it to just ln of x. Logarithmus naturalis of x, the natural log of x, i.e. the log base e of x. So whenever you see ln of x, you can always rewrite it as log, L-O-G, base e. And that might help you remember that it's just like any other log. But the nice thing about it is because it does occur in so many types of growth and decay in nature, it's pre-programmed into pretty much any scientific calculator and especially into our graphing calculators. So when you see this, y equals ln of x, you can rewrite it to be log base e of x, and then you can rewrite that in exponential form, right? E is the base, y is the exponent, and x is the result. So if you rewrote it in exponential form, it would look like this. E to the y equals x. So you may notice the only difference between log base e and the parent function we just did is the location of x and y. So when you have y equals e to the x, which is the function we just graphed, that's when x is the exponent and y is the result of a base e. But when you have y equals natural log of x, ln of x, which is a log base e of x, that's when y is the exponent and x is the result of a base e. So when I do a table of values for a natural log function, I'm going to want to go ahead and switch the x and y's from the e to the x function. So the -2, -1, 0, 1, and 2 part will actually now be the y value because the y is the exponent. And then the result, right? Because x is equal to e to the y. So the result of those base e's to those exponents becomes your x value, the number in the natural log. So this was the 1 over e squared. This was the 1 over e. This was 1. And then this is just e, and then the last one should be e squared. E to the power of 2 is e squared. So basically the x and y from the exponential function of e to the x have just switched. But let me show you here. Let me just go ahead and plug these in. So if I did ln of e to the -2, you could try it on your calculator. It should give you -2. Okay? If I did ln of e to the -1 in my graphing calculator, it should give me -1, or even on your scientific calculator. If I plug in ln of 1, I should get back a 0. Ln of e should give back a 1, and then ln of e squared should give back a 2. So these are now your outputs, right? The exponents from the exponential function that we just did a minute ago become the outputs of this natural log function, because the natural log function is the inverse of e to the x. And so the input and output of e to the x, that function specifically, have switched. So that's why I have to be careful about what I plug into a natural log. What I plug into a natural log has to be the result of raising a base e specifically to a power. So notice these numbers are always greater than 0. Right? Because they become like, these ones are small fractions. 1 over e squared, that was like 0.14, right? We found that out a minute ago. 1 over e was about 0.4. They were positive and close to 0. Meanwhile, over here, this was like 7.4. These values get bigger and bigger, further away from 0 as the exponent gets more positive. So these are the numbers going into the natural log. The things going inside the natural log are these values here, and then out will pop the exponents. So when you plot it, it'll be a reflection of this graph over the line y equals x, because the x and y values have switched. So now I will go to the right about 0.14, so barely to the right from the origin, and then down 2. For the next point where it was 1 over e, which is about 0.4, so I'll go a little further away from the origin and then down 1. For the third point when the input was 1, right, e to the 0 was 1, the output, or the exponent that made that happen, was 0. So I have a point at 1, 0, which is our typical x-intercept for any log of any base. When I had an input of e, ln of e was 1. Now e is about 2.7. So when I go a little bit, closer, just between 2 and 3, closer to 3, right, 2.7, the output is 1, because e to the first power, right, the y values are the exponents, so e to the first power equals itself. And then when I go to about 7.4, if I have room here, 1, 2, 3, 4, 5, 6, 7.4, like right around there, I will go up to 2, right there. And you get a graph that kind of looks like this. It has that typical shape of any log function with a base greater than 1. It has that typical x-intercept of 1, 0, which is true for any log of any base. And it has a vertical asymptote along the y-axis, or the line x equals 0, just like any other log function of any base. And that's because x and y are switching, because the natural log of x, or log base e of x, is the inverse to e to the x. Then anything that that belonged to y before, like even the asymptote, now belongs to x. So before we had a horizontal asymptote along the x-axis with the equation y equals 0. That switches. Now it goes along the y-axis with an equation of x equals 0. So log functions, including log base e, which is abbreviated as ln of x, have a vertical asymptote at x equals 0. So now the domain has to stay greater than 0, because the domain are the results, what you get after you raise e to a power, which is only going to ever be positive. So now the domain and range are switching, right? Before, the range was what had to stay positive. We switched that now, though, and so now it's the domain that stays positive. And before it was the domain that could be any real number, right? When I plug -2 and -1 and all that in for x. Well, now those values are your outputs, the y values. So the y values are what can be any real number. And the ordered pair of the y-intercept switched, right? The point 0, 1 switches to become an x-intercept of 1, 0. This function is increasing over its whole domain, but notice its domain doesn't even begin until after 0, not even including 0, which is why I have a parenthesis here. So from 0, to positive infinity, because the function moves to the right toward positive infinity, on that interval we would say that this function is increasing. And again, that's because its base of e, which is about 2.7, is greater than 1. So let's work with some expressions that all involve ln, and remember that what they are is a log base e. So sometimes you'll be asked to evaluate expressions, right? Find the value of. And these tend to really scare students because they have all like letters, L and N and E, and it's like, what is happening right now? So remember, this ln is just short for log base e. And then another thing you have to remember is that whatever the log equals is the exponent of the exponent, whatever you raise the base to get the inside. So this is kind of like saying e to what power would equal e to the third? Hopefully it's obvious. Well, that power has to be 3. E to the third equals e to the third, right? E raised to the power of 3 would equal e raised to the power of 3. So this log is equal to 3. This exponent here is equal to 3. So basically what happens, because these are inverses of each other, the natural log and the base e will cancel each other out and leave you with whatever the exponent was, right? Because it's a log base e. So log of same bases will cancel those bases and leave you with just the exponent. So the answer for this is 3. Okay, now again, I see ln of 1. And so I have to remember that's a log base e of 1, right? This is an abbreviation for log. It's a log. What's a log? A log is an exponent. So I'm looking for what the exponent is. E to what power is equal to 1? Well, the only way you can raise something, the only number you can raise something to get 1 is 0. E to the 0 power equals 1. So you kind of have to think backward, but then, you know, that's how we do this. So e to the 0 power is 1, so therefore ln of 1 is 0. Because the log is the exponent, and e to the exponent of 0 equals 1, which is the result. Therefore, the exponent was 0. Okay, so here, where I have ln of e to the power of 2, I have to think of that as a log base e. A log base e of e squared, and then whatever that number is, I will divide it by 6. Well, you could just kind of take the shortcut and say, okay, well, they have the same base, so they must cancel and it equals 2, right? So then I get 2 over 6, and then my final answer is 1/3. Or you could just think about it, because we have to remember the log is the exponent. So if I'm trying to think, okay, log base e of e squared equals what? I have to think about what power. This is the exponent, right? What exponent do I raise e to? E raised to what power equals e squared, right? E raised to what power equals e squared? And hopefully right away it would be super obvious. Oh, I'd have to square e. I'd have to raise it to the second power to get a result of e to the second power. And then you would arrive at that answer of 2, right? Because the log is the exponent. And since e had to be raised to the second power to get e raised to the second power, then the exponent that I raised e to must have been 2. And then I divide by 6 and get 1/3. So that's evaluating. And then the other thing I wanted to emphasize is that ln, again, is just short for log base e. So that's really the whole point of this lesson, is that ln of x is really just short for log base e of x, or ln of whatever is short for log base e of whatever. In other words, it acts just like any other log. I can use the same properties. I can use the product, quotient, and power properties of logs because the natural log is a log. So it follows all of these 3 properties, product, quotient, and power. So here I see I can have a 5. That 5 can be brought inside to become a power of 3, right? The natural log of 3 to the 5th power, okay? Because I'm using the power property of logs, and since the natural log is just like any other log, it's a log base e, it follows all those properties. And then here, I see there's a subtraction going on between these 2 natural logs. And so what that means is that I'm going to divide the things inside the logs, right? That's what you do when 2 logs are subtracting. You divide the amounts inside to get them to combine. And then since I have a common factor here of 3, that one's going to cancel, leave me with 1, and then I'll only have 4 factors of 3 left in the denominator. 1 over 3 to the 4th. ln of 1 over 81. That's if I wanted to write that as a single expression with ln of x. So this is a numerical value, right? This one is just a number that I could evaluate in the calculator. This one here is more of an expression. But again, it's just using the product, quotient, and power properties that belong to any log, including log base e, which is what ln is short for. So first thing I notice is this 1/2, and it's applied to this whole sum. So maybe I'll do the sum first. We'll do order of operations. We do what's in the parentheses first, and then we deal with coefficients. So I'm going to use the product property here, because when 2 logs, which is what ln is, are adding, when 2 logs are adding, then the thing inside those logs multiply together. You take the product of the inputs. Okay, and then I'm noticing here there's a 4 outside of this ln, so let me just go ahead and bring that inside and make it an exponent of c. So now I have minus ln c to the power of 4. Okay, then I also have this 1/2 in front, which is the power of all of this. It was applied to all of it, right? So it's the power of not just b, but a and b. So now I have ln of the whole quantity ab raised to the power of 1/2 minus ln of c to the 4th. Well, I hope you're remembering what a 1/2 power is. A 1/2 power is a square root. The denominator of the fraction is the root, and since it's a 2, it's a square root. So now I have ln of the square root of a and b minus ln of c to the 4th. Now, last but not least, I'm going to use the quotient property because it's a natural log, which means it's a log base e, so it follows all the same properties. And so I'm going to divide. I'm going to do the square root of ab divided by c to the 4th because the logs themselves were being subtracted. Therefore, the thing inside the log should be dividing. Using the same properties, natural logs can expand. So if you have 2 things multiplying together inside a log, you can use the product property here to expand them. So this would give me the natural log of 5 plus the natural log of e, because I can use the product property to take the sum of the 2 separate logs. But then the natural log of e is just 1. Why? Because the natural log is a log base e, and a log of any base is equal to the exponent of that base, whatever exponent you'd have to get to result in whatever's inside. So if we're trying to figure out what that is, e to what power equals itself, hopefully right away you'd think, oh, e to the first power would equal e to the first power, right? The log is the power. So the natural log of e is a log base e of e, which is equal to 1. So this ends up equaling, when all is said and done, the natural log of 5 plus 1. This guy over here, ln of 1 over 8, I could expand that and make it ln of 1 minus ln of 8. Why? Because it's a log. It's a natural log, but a log is a log, and it can follow the same properties that all other logs follow. So when you have a quotient of two things inside a log, you can split that and make it subtraction of the two separate logs. But then the natural log of 1 is 0. So I get 0 minus the natural log of 8, or just simply the negative natural log of 8. Lastly, I will conclude this video by solving a few equations. This may involve our calculators to get a decimal value for. But these equations are all either going to be utilizing the natural log or utilizing a base e, and helping you get comfortable with your calculator and working with these values. So, like any other log equation, when you have equations like this where you have some pieces with logs and some without, what you want to do is combine all your log expressions into one. Condense into one using properties of logs. So I'm going to use the product property on this one and get ln of 4 times x plus 1. So I multiply the two inputs of these logs that we're adding previously, and that combines them into one log, and that equals 2. And then I have to remember what ln stands for, right? It's abbreviation for a log base e. And while we're at it, I'm going to go ahead and distribute the 4 inside the log there. And then it's right at this point where you remember it's a log base e. You've got log base e of this inside equaling a number. This is where students often forget what to do, so you want to make a big deal about it in your notes so you don't forget. You rewrite your equation into exponential form, which is why it's so important that you remember what the natural log is an abbreviation for, because you have to know what your base is. And it's abbreviation for a log base e. So what I'm going to do is rewrite this using my base e raised to the power of 2, right? Whatever the log equals is the exponent. And that results in this expression of 4x plus 4. And then from there, we're just trying to isolate x. So from there, I would subtract 4 to both sides. So I get e squared minus 4. And then I divide both sides by 4. So I've got my two answers. I've got my exact value. Let me write them here. Well, let me box this first. So I have my exact value answer, which is equal to e squared minus 4. And then all of that divided by 4. And then I have my approximate value, which is what I would get if I plugged that into a calculator. And I get an approximate value of 0.847. Whenever we're approximating values, let's make sure to round them to 3 decimal places. So as an exact value, that's e squared minus 4 over 4. As an approximate value, that's 0.847. So we'll do a similar process over here with this log, although we're going to recognize these coefficients in front. But I want to combine these into one log expression, a single log expression. So I'm going to take this 2 and make it the power of x. I'll take this 3 and make it the power of 2. And so I will have the natural log of x squared plus the natural log of 2 cubed. And then all of that equals 5. Okay, so then that equals the natural log of x squared plus the natural log of 8. And then because of this addition, I can use the product property to go ahead and multiply the 8 and the x squared together. So now I have the natural log of 8x squared equals 5. And it's right at this juncture that I can go ahead and rewrite into exponential form. Once I get one log on one side and then another value on the other side, this is when we rewrite into exponential form, but we also have to remember that a natural log is a log base e, because I have to know what my base is if I'm going to rewrite into exponential form. So let me do that over here. So I have a base e, so that's my base, and then it's being raised to the power of 5. Whatever the log equals is the exponent, so 5 is the exponent, and then the 8x squared is the result, right? Whatever's inside the log is the result of raising e to the power of 5. So now I just need to isolate x. So I'm going to divide both sides by 8. And then I'm going to square root both sides. So this will be interesting. So I have e to the 5th equals x squared, and I need to get x by itself. So I have to do another inverse. I'm using two inverses. I'm using an e to the x inverse, and then I'm using a square root to cancel out the square. Now normally we would do plus or minus. Normally we would do plus or minus, except that when you're looking at a value of x that is also inside of a natural log, it's the domain of a natural log, we can't allow that to go negative. So in this instance, I'm only going to want the positive root. So my exact value, so I have two values, right? My exact value would equal, so x would equal the square root of e to the 5th over 8. That's my exact value. And then the approximate value of that would be what I get when I plug that all into a calculator. And whenever we approximate, we should round to 3 decimal places, so that would be 4.307. Okay, so that was solving equations that contained an ln in them, a natural log. Now we're going to use the natural log to solve equations that have a base e. So this one's kind of already ready to go. It's got a base to a power equaling a number that doesn't have a common base with e. So what I'm going to do here is rewrite into natural log form. Rewrite into logarithmic form. So basically we're using these inverse relationships to just go ahead and get this exponent into base level. So we're going to use a log of base e, since that's my base, of 12, right? So the result goes inside the log, and then the log itself equals the exponent. So this is how we solve exponents. Now remember, a log base e, that's just ln. We can abbreviate that as ln. So ln of 12 equals 3x, and then I'm going to go ahead and divide both sides by 3. So I have an exact form. My exact form equals ln of 12 divided by 3. Now if I plug that in a calculator, that'll get me my approximate form. And we'll round that to 3 places, 0.828. Okay, so last but not least, we will solve example 13, which is an exponential function with a base e. But what I want to do is isolate the base. Okay, we want to isolate the base. So there's a lot of things around the base e that need to be moved away. So I need to start by subtracting 3. And then I get to here, 4 times the base e to the power x minus 1 equals 68. Then I divide by 4 to get the base all the way by itself. And then I get e to the power of x minus equal to 17. And then it's right at this juncture that I rewrite into log form. I'll kind of abbreviate that. But we're going to rewrite into log form using a log base e. A log base e of the result, right? The result was 17. That goes inside the log. And then the log itself is equal to the exponent, x minus 1. So here's what I have. I'm going to move this up here. So now I have the natural log, right, because that's what log base e is. The natural log of 17 is equal to x minus 1. So all I have to do at this part is add 1 to both sides. And then I get my exact answer, which is just the natural log of 17 and then plus 1. That's my exact answer. And then that answer is approximately equal to, if I round to 3 places, it's about 3.833. And that is really sums up the functions of e to the x and the natural log of x and their relationship with each other. I'd like you just to try a few problems before calling it a day. So pause your video here, see if you could work these out, and then check your answers. Okay, so here are the answers to the U-tries. For the first one, I got e to the 8th minus 3 over 2, which was about 1,488.979. For 15, I had a strange looking answer. It was the natural log of the quotient, 25 over 18, and then all of that divided by 0.04, which as a decimal wasn't that bad. It was about 3.547. For 16, first you had to make 2 a power of b and then 1/3 a power of c. So we ended up with a b squared and then a c to the 1/3, which was actually a cube root of c. And then I combined ln of a and ln of cube root of c as a product, since those logs were adding. And then divided all of it by b squared, since that log was subtracting. Lastly, for 17, my final answer was -1. I used the quotient property to split it up, ln of 1 minus ln of e. But ln of 1 is equal to 0. E to the 0 equals 1. And ln of e is 1. E to the first equals e. So it actually just became 0 minus 1, which is -1. Or you could think of that as e to the power of -1 equals its reciprocal. And the log equals the exponent. So the natural log of 1 over e, or the reciprocal of e, would have to equal -1. That's it. Thanks for tuning in for this entire video. It was a lengthy one. And tomorrow you'll be able to practice some more. Thanks.